Welcome back. In our last episode, we explored the basics of altimetry, how altimeters work, the meaning of QNH and standard settings, and why pressure and temperature matter. Now let's continue with advanced altimetry, including RVSM, vertical separation, and modern navigation systems. Let's begin with RVSM, reduced vertical separation minima. This is a set of rules that allow aircraft to fly with only 1,000 feet of vertical separation between flight levels from FL 290 to FL 410. It increases airspace capacity and efficiency. Before RVSM, aircraft above FL 290 required 2,000 feet of separation due to potential altimeter errors at high altitude. But with modern instruments and strict maintenance standards, regulators approved reduced separation, doubling the number of available flight levels. To fly in RVSM airspace, your aircraft must be specially certified. It needs dual altimeters, an autopilot capable of holding altitude precisely, a transponder with mode C or S, and systems that meet strict accuracy and redundancy standards. Pilots also need RVSM training. This includes understanding altitude monitoring procedures, how to detect altimeter discrepancies, and how to report deviations. If anything fails in flight, like an altimeter or autopilot, you must exit RVSM airspace as soon as possible. Let's talk about altimeter error sources. Barometric altimeters rely on air pressure, but pressure isn't perfectly linear. Factors like instrument hysteresis, mechanical friction, and lag can cause small errors. Modern digital systems reduce these, but they still exist. In RVSM, allowable altimeter error is usually plus or minus 200 feet between the two systems. Pilots must monitor both altimeters during cruise and log discrepancies. If the difference exceeds limits, ATC must be informed and vertical separation increased. Another key concept is altitude deviation. This can happen when temperature, pressure, or system failures cause the aircraft to drift from its assigned flight level. RVSM monitoring systems detect this automatically and alert the pilot or controller. To minimize risk, pilots must cross-check altitude constantly. Compare altimeter readings with flight director, autopilot, and GPS data. Also, verify level-offs during climb and descent. A 200-foot deviation at FL 350 may seem small, but it's a serious issue in RVSM. Let's explore transition altitude versus transition level. Transition altitude is the point where you switch from local QNH to standard pressure when climbing. Transition level is where you switch back to QNH when descending. The space in between is called the transition layer. In some countries, the transition altitude is fixed, often around 5,000 feet. In others, it varies by airport and weather conditions. Always check your charts and ATIS to know the correct transition point and avoid altitude mismatches. Speaking of mismatches, let's talk about altimeter setting errors. Using the wrong QNH can lead to vertical separation violations or even CFIT, controlled flight into terrain. Cross-check ATIS, META, and ATC clearance to ensure your altimeter is set correctly. Modern avionics often display GPS altitude, which is based on a geodetic model of the Earth, not pressure. While useful, GPS altitude isn't used for separation, it doesn't reflect terrain clearance or standardized pressure levels. Use it only as a backup. Some systems now integrate BaroVNAV, a system that uses barometric data to guide vertical paths during RNAV approaches. This provides more precise descent paths and can even allow non-precision approaches without traditional ground-based aids. But BaroVNAV has limitations. It assumes accurate temperature and pressure. If conditions deviate too far from standard, approach minimums increase or BaroVNAV may be restricted altogether. Always check NOTAMs and temperature limits in cold weather. Let's touch on TAWS, terrain awareness and warning systems. These use GPS and a terrain database to predict if the aircraft is at risk of controlled flight into terrain. They work best when barometric and GPS altitudes match expected values. TWS can save lives, but it's only effective if your altimeter is set correctly. A misset QNH could delay or prevent terrain warnings. Always ensure your settings are up to date and cross-checked when operating in mountainous terrain. In busy airspace, accurate altimetry is also crucial for vertical separation. Whether you're flying VFR or IFR, maintaining assigned altitude prevents conflicts. Controllers rely on your Mode C or Mode S transponder, which sends your altitude data automatically. Altitude reporting errors can occur if your encoder is faulty or incorrectly calibrated. If ATC reports a mismatch between your assigned and reported altitude, investigate immediately, reset systems, reselect transponder mode, or switch altimeters if necessary. In some regions, pressure corrections are required at low altitudes. For example, if the QNH is very low, say below 980 HPA, controllers may assign pressure-corrected altitudes to ensure terrain clearance. Always follow these instructions precisely. Now let's consider cold temperature operations again. ICAO and national authorities may designate specific airports or runways where cold temperature corrections are mandatory. These help ensure that aircraft don't descend below minimum safe altitudes on approach. Approach charts will sometimes show a snowflake symbol snowflake hash indicating that you must apply corrections when temperatures fall below a certain threshold. Use published tables or approved apps to calculate the required adjustment. Altitude accuracy is also affected by static port location. On some aircraft, airflow distortion can cause pressure reading errors, especially in uncoordinated flight or strong crosswinds. That's why design standards and flight testing are so strict for RVSM approval. Let's review the big picture. Altimetry is about more than just knowing your altitude, it's about ensuring separation, safety, and system integrity. Every stage of flight, from taxi to cruise to final approach, depends on accurate pressure settings and monitoring. In the future, we may see more reliance on satellite-based altimetry. Systems like ADS-B and GNSS are already supplementing traditional barometry. But for now, pressure remains the backbone of altitude measurement, and every pilot must understand it thoroughly. Let's recap. RVSM enables 1,000-foot separation between FL 290 FL 410. Aircraft and pilots must be certified to fly RVSM. Altimeter errors must be monitored and logged. Transition altitudes and QNH settings must be verified. GPS and BaroVNAV offer support, but pressure remains essential. In the next episode, we'll continue with altimetry, part 3, where we'll tackle altitude busts, temperature deviations, and how ATC manages vertical separation in different classes of airspace. It's the final piece of the altimetry puzzle. See you in Meteorology number 11, Altimetry, part 3.